In this video, I will explain all the AI buzzwords that you are seeing on the screen, but I will do so in very plain English and visually, so that you won't forget them. And I will also give you the big picture context of these concepts, why they matter to the economy, to society, and to your future. In part 1 of this video guide, we began with the overarching buzzword of AI, and then went through the series of Russian dolls until we reached the large language model. The link is here in the right hand corner in case you want to watch it. This second video builds on that. As we saw, the LLM is the type of artificial intelligence that powers apps like ChatGPT. But we also saw how LLMs are a bit like the sorcerer's stone of the AI industry. Because many experts and corporations believe that LLMs are not just great for our current use cases like chatbots, customer support and things like that. The endgame for these big tech companies is even more ambitious than software that can talk. They believe that LLM technology will soon lead to two other massive milestones. First, AI agents, which will be able to replace some white-collar jobs and, when combined with robotics, some blue-collar jobs too. Second, AGI, which is full human-level AI, and will be able to replace virtually all white-collar jobs and blue-collar jobs. And I know that when we reach this point, it's easy to feel that this sounds like science fiction. So please, don't just take my word for it. Because these companies have clearly spelled out that scaling this AI software until it reaches full human level is their endgame. Here's Logan Kilpatrick, one of the top figures of OpenAI at the time, saying candidly what that AGI that they are trying to build is.
What is an AGI?
Yeah, so AGI is artificial general intelligence. OpenAI's definition of AGI is when these artificial intelligence systems are able to do all economically viable work that a human is able to do. All economically viable work that a human is able to do.
And I'm starting with all this context before going into the buzzwords, because more and more of the artificial intelligence buzzwords that you are going to hear these days and that I cover in this advanced buzzwords video are related precisely to scaling LLMs. That means making them bigger so that they can become smarter. Everyone in big tech, and increasingly more politicians and governments too, are becoming obsessed with how to scale LLMs. So the next few years are gonna revolve around the AI concepts that I will explain today. Okay, let's get started. The three pillars of LLM intelligence. We are going to start from the most zoom-out view of how LLMs get bigger and smarter, and then go into the details of each aspect. The main three things needed to make LLMs smarter are data, compute, and algorithms. Progress in these three elements was necessary to go from where we were just a few years ago, when LLMs could hardly string a sensible sentence together, to now, when LLMs speak as articulately as a very smart human. And progress in these three is also considered to be able to take us even further, to AI so smart that it will be able to replace the majority of labor. Out of the three, algorithms is probably the least well understood by the mainstream public. But at the end of the day, you just have to think about them as another way in which AI scientists refer to the software aspect of LLMs. Because as it happens, all computer software is made up of algorithms. Algorithm is just the fancy word used in computer science to say step-by-step guide. And all computer software is just an accumulation of many of these step-by-step guides. For example, the software behind a web browser comprises lots of step-by-step guides. One of those instances could be the algorithm for the back button. That algorithm would go something like this. If the user clicks, then access the list of all visited websites, then select the most recent item in that list, and then load it on the main browser window. Likewise, AI software is like any other type of software. It is also made up of algorithms. The next element is compute, which again is just the specialist term to refer to something you know very well, hardware. If algorithms can be seen as the software aspect of LLMs, compute is the hardware aspect. Compute means all the computing resources like processing power, memory, etc. that we need to run the LLM software. The key here is that one of the ways to make LLMs smarter is by making them bigger. And to make them bigger, you need more powerful hardware to run them. That's why the power of our hardware also contributes to LLM progress. Because the more powerful our hardware gets, the bigger and smarter are the LLMs that we can run. And finally, data. If you remember from the previous video, we saw that LLMs belong to a type of AI called machine learning. The characteristic of all machine learning is that it learns about how the world works, not because the AI engineers put all that knowledge inside the AI software directly, but because they give the AI software data from which to learn about the world. A bit like a teacher gives you information and recommends books for you to read, but he can't open your brain and put that knowledge inside you directly. Similarly, machine learning, including LLMs, derive all their knowledge from the data they are given to learn from by the AI engineers. For that reason, whenever we give them more or better data, LLMs can learn more stuff and they can become smarter. That's why data is the third driver of LLM progress. Scaling versus algorithmic progress. But is it necessary to make progress in the three ingredients in order to make LLMs smarter? Or is it enough to improve just one or two of them to make LLMs more intelligent? The answer is yes, it is enough. And here is where another important AI buzzword comes in: scaling. You will hear all the time journalists asking AI experts, do you think we can reach AGI with just scaling, or we also need algorithmic progress? What do they mean? What they mean is that you don't need to improve the three ingredients to make LLMs more intelligent, because you can also make them smarter by just making them bigger or by just improving their design. Making them bigger is what is known as scaling, and improving their design is what you will hear referred to as algorithmic progress. So even if there is no more progress in how the LLM software is designed, by just using the current designs and scaling them to a bigger size, it has been found that they also get more intelligent. And many AI scientists and AI CEOs like Ilya Sutskever and Sam Altman believe this will continue to happen. They think LLMs will continue getting smarter by just throwing more compute and more data at them, possibly going as far as reaching full human-level intelligence by scaling alone, even if there are no big breakthroughs on the design side. This has enormous big picture implications. One is good and one is not as good. The good one is that sourcing more data and compute is much easier than making software breakthroughs. Breakthroughs in software, like in any other discipline, are unpredictable. In the same way that we cannot know when we will find a cure to cancer, we also cannot be sure when we will find AI algorithms that are better at learning than the current ones. On the other hand, making the current designs bigger by scaling them with more hardware and data is for the most part just a matter of money. So it is expected that AI progress will be quite steady over the next few years. As for the bad news, it is also that it is just a matter of money. Unlike other technological revolutions like the internet, that allowed anyone to create a small business that could end up taking down the big incumbents, in this revolution the biggest advantage goes precisely to the corporations that are already ultra-rich. Because only those that have lots of money to buy huge amounts of hardware are able to build the most powerful LLMs. And those particularly well-placed are, of course, the big tech giants, that not only have the money, but also oftentimes already own vast amounts of data and compute. The greatest success stories of the internet revolution were about small new players that disrupted the businesses of the old giants. This time, however, the story is very different. Behind every powerful LLM, there is a tech giant who either owns it fully or is a big investor funding the lab that created it. Big data. Let's dive first into the easiest to understand of the three ingredients: data. There are fewer popular AI buzzwords regarding data, so this one will be quick. Probably the most frequent buzzword you will hear is big data, which is sometimes used instead of data. Big data is a term used in computer science and business that simply means data in such a large amount that normal software and hardware can't handle it. Normal amounts of data can be analyzed with normal software like an Excel sheet and can be stored and processed in normal computing hardware. But when we get to big data amounts of data, then we need special software and hardware and specialist engineers to deal with it. Big data is not a concept exclusive to AI. It is any extremely large amount of data in any industry. For example, the entire YouTube library of videos is big data because it requires special approaches to store, manage, and maintain the monstrous amounts of video that YouTube holds. By the way, if you find the big picture of AI useful to you, remember to support this channel by subscribing to it and by liking this video. Thank you. So that was big data in general. And in the specific context of AI, the term big data is used when we want to highlight the monumental amount of data that has to be fed into these LLMs. For example, an LLM like the one powering ChatGPT needed to read billions of pages of text in order to reach its current level of intelligence. By the way, two other important buzzwords connected to this are training and inference. Training is the term we use for the period during which the LLM is learning. So it is during training that the LLMs are exposed to all that data from which they learn all the things they know. On the other hand, inference is when the LLM has finished its education and is ready. Inference is when people and companies use the LLM. For example, every time you ask a question to an LLM-powered app like ChatGPT, the processing of answering your question is what we call inference. So in the context of training and inference, the stage at which big data is required is during training, during the process of learning. And actually, the reason for the success of LLMs is that unlike in previous periods, now LLMs can learn from those gigantic amounts of data freely available on the internet that we didn't know how to exploit before. But why couldn't all that data be exploited before? Well, this leads us to another two AI data concepts: raw data and labeled data. Raw data is just untreated data. You just gather a bunch of files containing info and feed it to the model as it is, without further explanation. Labeled data, on the other hand, can be seen as explained data. Before feeding it to the AI model, data is neatly organized into pairs of an input piece of data and a target outcome. The target or desired outcome is what we call the label. The typical example for labeled data is a collection of pictures of cats and dogs in which you've carefully added to each image a piece of text indicating whether that animal is a cat or a dog. The words cat and dog would be the target label. The great thing about labeled data is that, in general, it is easier for AI software to learn from data if it has these labels. Following our cat and dog example, a neural network can learn very quickly what cats and dogs look like if the data is labeled, and then can tell you if some other photo contains a cat or a dog. And this ability to recognize cats and dogs is present even if the neural network has never seen before the pet in that new image. This ability of AI models to apply what they learned during their education to new things that they've never seen before is another essential buzzword: generalization. For example, when you hear things like "this bigger LLM generalizes better than the previous model," they mean that this LLM can better apply what it learned to new questions or new tasks that it had never experienced during its training. The ability to generalize is a key cognitive characteristic of both biological and artificial intelligence. The one bad thing about labeled data is that it costs money and time to create the labels, especially in the amounts that AI needs. There's only so much labeled data available, and creating more of it is super slow and expensive because for the most part, labeling data requires paid human labelers. The good news is that recently we found a way to make LLMs learn from raw data, almost as well as if they were learning from labeled data. And that's why for the first time in history, AI could finally learn from all that raw text data that is freely available on the internet. Later on, we'll see how this magic happens. And speaking of text, all the impressive learning about how the world works that these models have acquired was mainly based on written information about the world. However, more and more progress is being made at using other types of data, like images and videos. When an LLM is trained on more types of data and not just text, they are called multimodal LLMs. At some point, all state-of-the-art LLMs will have learned not just from huge amounts of text, but also from huge amounts of images, audio files, and especially millions of hours of video. This multimodal learning will further accelerate their understanding of the complexities of the world. But don't get me wrong, this doesn't mean that text-educated LLMs don't understand anything about the visual world. In the same way that the biological neural network of a blind human compensates for the sensory inputs it doesn't have, LLMs trained on text have also compensated for their lack of vision. In fact, anyone who has chatted with an LLM knows that they understand visual concepts very well. However, it is expected that when we get better at using video to teach them, their intelligence will explode even further, due to the vast amount of concentrated knowledge about the world and its physics that is contained in video data. The big picture implication of this central role of data is that right now a data war is starting. Since companies have realized that data can be literally transformed into synthetic intelligence, they are erecting data walls so that only they can train AI on their data. One example, X, Elon Musk's social network, has recently made two important strategic moves in this direction. First, blocking automated bots from scraping its textual content. And second, incentivizing video creators to post on X more often, so that X too can build a YouTube-style video library that will be critical to train the next generation of multimodal LLMs. The two main types of algorithms. Now it's time to zoom into the algorithms, and you know something about them. There are two very different types of algorithms, and yet most educational AI content mixes them up or doesn't stop to explain the fundamental difference. It's a bit of a confusing mess, but worry not, because I'm gonna make it crystal clear for you. The two main types of AI algorithms are the architectures and the algorithms from the learning paradigms. And I have found a useful metaphor to visualize the big picture difference between these two types of algorithms. They can be seen as students and schools. The architectures are simply the students, the actual parts of the AI software that learns. So different architectures like neural networks, decision trees, support vector machines, etc. lead to different types of students. On the other hand, we have the groups of algorithms that we use to teach those AI students, or as they are referred to more frequently in AI, the learning paradigms. The learning paradigms can be seen as different schools with different educational methods. And by the way, what we saw in the essential buzzwords video was mostly centered around the architectures, because the most frequent buzzwords in AI are related to the architectures, so I started with those. As a quick recap, we saw that the neural network was indeed the most successful architecture within AI. And the neural network is the most popular type of architecture for the simple reason that it is the smartest. It is the smartest type of student that we've managed to build so far. Then within neural networks, we saw that the most successful architecture was the deep neural networks. And that within those, the most successful architecture was the transformer deep neural networks. And finally, we saw that when we make the transformer neural network architecture very, very big and train it on lots and lots of text data, we call those huge architectures large language models. In this video, however, I'm finally going to go inside the schools. But before that, I want to mention the last important buzzwords about the architecture. This will be super useful later to understand how the schools work. In the guts of the neural network. What can be found in the guts of neural networks? Whatever is in there that makes them able to learn concepts and acquire skills. I'm going to tell you, and by the way, what I'm going to say applies to both neural networks in general and LLMs in particular. So, as we saw in the previous video, neural networks are pieces of software that simulate a very simplified but very useful brain. These neural networks are made up of units, called artificial neurons or nodes, that are inspired by the neurons in biological nervous systems. These artificial neurons are organized in sets called layers, and the layers are stacked up in sequence. Also, the neurons in each layer are connected to the neurons in adjacent layers. This architecture is not as complex as the architecture of our biological neural networks. However, they operate on a similar mechanism. That mechanism is that both biological brains and artificial neural networks store knowledge in the form of reinforced connections between their neurons. If a concept or a skill is very important to the system, the connections that codify that concept or skill will get stronger. What I didn't mention in the first video is another essential buzzword: parameters. Parameters are simply the numerical values that are assigned to every neuron and to every connection between neurons. These numbers are so important because it is the way in which the strength or the weakness of the connections is represented in artificial neural networks. When the parameter has a higher value, the pathway is reinforced, and the signal is more likely to pass through that pathway. Conversely, lower values make the pathway weaker, and the signal less likely to go through. And that's why parameters, these little numbers, are so important, because they are the only way in which a neural network can store knowledge. In fact, the only difference between a newborn neural network that hasn't learned anything yet and a neural network that has as much knowledge as, for example, ChatGPT, is a file with a list of numbers corresponding to the numeric values for each parameter. The parameters file. That's all. And that's also why in AI, to compare the power of different neural network generations, you will hear people say how many parameters they have, because that amount indeed gives a strong indication of its capacity to store knowledge. For example, GPT-1 had 117 million parameters, GPT-2 had 1.5 billion, GPT-3 had 175 billion, and as for GPT-4, its exact number of parameters hasn't yet been made public by OpenAI, but it is believed to be 1 trillion or more. And I want to clarify something that could otherwise confuse you. You will often hear people refer to the parameters as the weights. This is because the parameters inside a neural network can be subdivided into two types: the biases and the weights. Biases is the name for the parameters assigned to each neuron, and weights is the name for the parameters assigned to each connection between neurons. When talking informally, AI people tend to use the word weights interchangeably with the word parameters, even if strictly speaking, that's not the same. For example, you will hear things like, "A hacker broke into the AI lab and stole the weights file." What they mean is that they've stolen the whole parameters file with all the values of the weights and the biases. And I'm making this clarification because you are going to hear this kind of conversation more and more. Because actually protecting the weights is becoming more and more critical. The numerical values of the weights and biases are the only difference between the newborn LLM that knows nothing and an educated LLM that has gone through all its big data education. The rest of the LLM architecture remains completely unchanged. The only thing that changes after those hundreds of millions of dollars spent in training the LLM is the weights file. Actually, at some point, as we get closer to AGI, it is believed that the AI labs will have to protect their weights with the same level of security that is now used to protect nuclear secrets at military facilities. Time to go to school. Now that we understand the architectures, we can see how those architectures go to school. The four most important learning paradigms for educating an AI model are supervised learning, unsupervised learning, reinforcement learning, and self-supervised learning. These four have become very famous buzzwords repeated all the time when LLMs are discussed, but to be honest with you, apart from AI engineers, almost no one really knows what they mean. So if you're watching this video, congratulations, because you are gonna have a more profound understanding of AI than 99% of people out there. But anyway, why are they called paradigms in the first place? The reason is that each paradigm represents a very different philosophy or approach to teach AI models about the world. For example, in the case of biological intelligence, you could teach a child by repetition or by games, by exploration, etc. Well, something similar happens with the learning paradigms that we use to teach AI students. Each one is a very different approach that applies different teaching algorithms in order to achieve the goal of educating the AI student about the world. Let's see each approach in turn. Supervised learning is the teaching approach in which we help the AI student learn about the data by labeling it. Yes, here is where the labeled data that we saw earlier comes into play. This supervised approach is great because those labels can be seen as explanations that help the student learn very efficiently from the data. The problem with this approach is that the labels need to be created by humans. So this type of school needs lots of human teachers labeling the data, and that turns out to be very expensive. Also, humans are very slow at labeling the data. As a result, we cannot feed as much data as we would like to the hungry AI students. Unsupervised learning, on the other hand, takes advantage of something the digital world is filled with: raw unlabeled data. This makes this approach very convenient, but unfortunately, it's only suitable for certain types of tasks. For instance, you can use unsupervised learning to discover patterns in raw data. You can train a model to identify specific patterns within that raw data. A popular example is finding outliers. A financial institution trying to reduce fraud can feed raw data about financial transactions into a special type of neural network like an autoencoder. And all those transactions are fed to the model unlabeled. There's no need to label them with any extra information. Instead, the model autonomously finds patterns within the complexity of the raw data, by, for example, flagging transactions that deviate from the norm, outliers. In summary, unsupervised learning doesn't require human labelers, and so it is very economical and fast to set up. But the problem is that it has limited scope of applications. Reinforcement learning. Reinforcement learning is the type of learn by doing educational approach. It's a bit like teaching a dog to do tricks. If they do it well, they receive a reward, and if they don't do it well, they don't. The reward guides them through the learning process, until the rewarded ability ends up getting encoded into the neural synapses of the dog, or in the case of the artificial neural network, in its parameters. AlphaGo and AlphaZero, the AIs that beat champion human players at Go and chess, were famous examples of reinforcement learning. But probably the best example to visualize how reinforcement learning works is video game playing AI. In this type of reinforcement learning, the neural network has only the following inputs and outputs. All the pixels on the screen are the sensory inputs about the world that the AI student receives. The game score is the sensory input about its goal, which is the reward that the AI student will try to maximize, and the combination of keystrokes are the only outputs or actions that the AI student will be able to make. In the case of this video game called Breakout, all the neural network can do is use the keystrokes left and right. So by just watching the effects that its keystroke actions have on the screen and also on the score, the neural network begins to learn about how that pixelated world works and what actions in it lead to the most rewards. As for the self-supervised learning type, this is a very important part of the success story of LLMs, so we will discuss it in the next section. LLMs go to school. The previous section explained the main ways to educate AI models, ways that can be applied to many different types of architectures. But this final part is about the education of just one type of architecture, the artificial megabrains, the huge neural networks known as LLMs, the most powerful type of artificial intelligence that we have ever created. And LLMs are so sophisticated and so smart, in part thanks to having the most sophisticated training process that has ever been devised in AI. It's so sophisticated that it has 3 different stages, in which 3 different learning paradigms are used. First, pre-training, which educates the neural network using self-supervised learning. Then fine-tuning, which educates the neural network using supervised learning. And finally, RLHF, using reinforcement learning. So, to use our school and student metaphor, it is as if the neural network, before it can become a fully useful adult, needs to go first to school, then to high school, and finally to college. This intensive 3-stage program of education ends up creating the technological prodigy that LLMs are. Let's see how the magic happens. Pre-training. The first stage, pre-training, shouldn't be confused with something unimportant or something that happens before training the LLM. As so many things in AI, the names we use are a bit confusing and often misleading, and this one is no exception. Pre-training is actually the most important part of training, and it is actually the part that creates the powerful raw intelligence and savant knowledge of the LLM. Also, during pre-training, it is when the big data and the big compute are required. The other two educational stages require much less compute and data. So yes, there's nothing pre or minor about pre-training. During this pre-training phase, the amount of information to which these neural networks are exposed is humongous. It's a very large chunk of all the information available on the internet, far more than any human being could possibly read in a lifetime. And we can feed so much info to these models because we feed it raw. No need for any humans to painstakingly label all that internet text. We just copy the data from the websites and directly feed it to the models as it is with very little pre-processing. But as we saw earlier, learning from raw data was called unsupervised learning and was very limited because it only had very specific use cases. So how can LLMs learn so much stuff and so many different skills just from raw data then? And here is where the fourth type of learning paradigm comes in. It was invented precisely together with the LLMs, or rather its invention allowed for the LLMs to be possible. This fourth learning paradigm is a very clever mixture of supervised and unsupervised learning that combines the strengths of both approaches into one. It is like unsupervised learning because it allows feeding raw data to the neural network. And it is like supervised learning because it actually does include labels, but the labels are created by the training algorithms of the AI software itself, not by humans. But all this is far too abstract. Let's see it in action with one example. The training algorithms of the self-supervised school transform all the text captured from the internet into chunks of text and then hide some words from those chunks. And that's what they feed to the neural network. So the neural network will receive the input "the capital of France is," with the final word missing and the label for the correct answer being Paris. In this way, little by little and with many different samples like this, it is trying to pair text fragments like "the capital of France is" with the most likely answers like Paris. And this is why you will have heard in the media that LLMs predict the next word. Because indeed, that's how they are pre-trained. They are pre-trained to become excellent guessers of the next word. By the way, you will sometimes hear predict the next token instead of predict the next word. We won't cover the term token today, but it suffices to know that it is a term that means something roughly similar to word. So although they are not exactly the same, they are so close that in AI we use predicting the next word and predicting the next token interchangeably. And a big picture inside here. Don't believe that the fact that these models predict the next word means that they are just autocomplete on steroids, as many critics say to belittle them. Because in order to predict the next word optimally, LLMs need to really understand how the world works in the first place, and also understand language. It is a very big but also very common mistake to think that these models simply memorize the questions and answers, because they don't. These models generalize their understanding of the training examples to language that they've never encountered before. So for example, if you give an LLM a sentence that you're sure that is not on the internet, something very convoluted like "the capital of the country in which the beautiful Lady Di died and in which the only European theme park created by the Walt Disney Company was built is," the model will know that the answer is Paris. Not because it had memorized that sentence that I've just made up, but because it had learned two things during its pre-training. It learned 1. Lots of facts about the world, and 2. How human language works. So at the end of the pre-training phase, after devouring billions of pages of internet text, and after using hundreds of millions of dollars in computing power, the parameters inside the LLM have acquired values that encode an enormous amount of facts about the world and a profound understanding of human language. By the end of the pre-training stage, the LLM has become a savant, and yet it is a savant that has very little ability to communicate its knowledge. Its understanding is extraordinary. Its communication is crippled. The next stage fixes this. Fine-tuning. Pre-trained LLMs are geniuses. But if you were to use an LLM that has only gone to pre-training school, all you could get out of it is autocompletions. Those autocompletions sometimes would be very useful, but sometimes would be useless. To continue with our example, if after pre-training you gave the LLM the input, the capital of France is, the model would almost certainly reply, Paris. But if you entered the capital of Paris is, it would probably reply, France. And why does it answer that? Well, not because the model thinks that the capital of Paris is France. Actually, it knows that Paris is a city and that it doesn't have a capital because only countries can have capitals. But it can't possibly tell you because it has trained to just autocomplete. And it has gotten so good at autocompleting that it has even learned about the most common mistakes that humans make. It's learned common error patterns that we humans make, like sometimes switching things by mistake. And it has learned that the most likely completion in this type of switched erroneous sentence is France. It's such a savant that it even knows the most likely ways in which people mix up their words. But obviously this is not useful. When you talk to an LLM, you want truthful answers, not just predictions of the likeliest next word. And that's where the next two phases come in. They turn the savant but fairly unusable LLM into a skilled and truthful communicator. The first of these stages is fine-tuning, and here the teaching method to teach the LLM to be helpful is supervised learning. Remember that supervised learning was called supervised because humans have to create target labels for the data. In this case, the human labelers create examples of the type of question that users will be likely to ask. Then they attach to them target labels that contain the type of well-researched and sometimes very detailed correct answer that we consider an ideal answer for that particular question. Then they feed all those pairs of questions and ideal answers to the LLM. This process is very painstaking and costly since the human labelers need to research and very carefully craft high-quality answers in order to demonstrate to the model what a high-quality answer is. The great payoff of all this effort is that during this phase, the LLM begins to learn to be helpful and truthful. And we even give the model examples of when people ask things that don't make sense. That way the LLM also learns how to deal with those situations. That's why when you ask a fine-tuned model, the capital of Paris is, it will say things like, actually Paris is itself a capital city, specifically the capital of France. Let me know if you meant to ask something else. And all these fine-tuned communication skills are added on top of the previous knowledge the pre-trained LLM had. The new learning doesn't replace that knowledge, it builds on it. So the same LLM that had already adjusted its parameters to understand the world now readjusts its parameters even further to the new goal. Not anymore to simply predict the next most likely word, but to produce the most useful and truthful answer possible. The savant has now also become a skillful and truthful communicator. RLHF. As much as supervised learning is an amazing method, it has one big limitation. It's the same limitation that all supervised learning schools have. They require lots of human supervisors writing the example questions and answers. This is a problem because quality human labelers cost money and also are slow at creating those quality questions and answers. Fortunately, another super clever strategy was ideated by the AI scientists. AI scientists noticed that it is much easier for a human to decide if an answer is good than to come up with the answer from scratch. For example, the majority of us are better at noticing if a poem is good than at writing a good poem. So the AI scientists said, what if we use our humans for scoring answers instead of for creating them? And RLHF was born. In RLHF, the LLM enters a reinforcement learning school. And you remember how these schools work, right? The model learns by taking actions based on the sensory data and a reward. Well, in the reinforcement learning from human feedback school, the method is the same. In this case, the sensory input are the questions. The action that the LLM can take is to write an answer. And finally, the reward is how good the human scorers think that the answer is. In other words, the human feedback. That's why this method is called reinforcement learning from human feedback. Also notice that, once again, this stage builds on top of the previous one. And that's why this method is possible at all, because the fine-tuned LLM had already learned to give quite decent answers that can now be used in this new loop to start the reinforcement phase. At the end of this third and final school, the LLM has further refined its neural connections, its parameters, to become even better at understanding what humans consider useful, truthful, and ethical. This is why it is so difficult to get an LLM to, for example, help you build upon. Through fine-tuning, and especially through the rewards and penalties of reinforcement learning, it has learned not only to be helpful, but also it has learned about what humans consider unethical and dangerous. So to recap, pre-training is the phase that creates the brute force intelligence. Fine-tuning puts all this knowledge and cognitive skills of the savant to the service of being a great communicator. And finally, RLHF extends the fine-tuning process even further, taking the LLM the extra mile to make it even a better communicator that is even more aligned with what humans consider helpful, truthful, and ethical answers. Nobody expected that LLMs would work so well. Nobody expected that they would work so well so early. The combination of 1. The transformer architecture discovered in 2017. 2. Making that architecture very big thanks to lots of computing power. 3. Giving that architecture access to big data to learn from. And 4. The sophisticated educational process in 3 stages using 3 types of learning paradigms. All 4 came together to give us the technological prodigy that LLMs are. But what about compute? In this video we've zoomed into data and especially into the algorithms, but what about the compute buzzwords? Well, this video is getting far too long to cover all the buzzwords related to compute. Also, the compute aspect of LLMs includes lots of geopolitical stuff, like the Taiwan problem, the China versus US race, etc. So it deserves its own special video. So if you like understanding the full big picture of AI like very few people can tell you on YouTube, subscribe to my channel. Anyway, thank you so much for watching and see you next time.